Hello, thank you for being here at the this webcast today. This is the National Municipal Stormwater Alliance Pond webcast series. This is the first in the series, The Problem with Ponds. And we have about 111 people showing up, so that's great. Thanks for registering and coming out to this event, making this time available. So a quick overview of what we'll be talking about. My name is Seth Brown, and I'm the Executive Director of the National Municipal Stormwater Alliance. I'll provide some opening information and remarks, and provide some context of what this is about and the series focused on pond issues. And we'll also have an overview of a draft product that we've developed called the Stormwater Pond Decision Framework. And that will be presented by myself and Randy Neprash, who's the vice chair of our organization. Then we'll have a panel presentations and discussion focusing on research related to pond problems, specifically PAHs and pond sediment as one specific problem that will be focused on. Then phosphorus release from ponds, and lastly, climate change and pond capacity and design. And lastly, we'll have a Q&A and wrap up at the end of those panel presentations. The specific speakers that we'll have today, I mentioned Randy Neprash. He is with Stantec, and he's also the head of the Minnesota City Stormwater Coalition, as well as the vice chair of NMSA, or the National Municipal Stormwater Alliance. Dr. Barbara Mahler will be presenting with USGS, and we'll also have Dr. Glenn Moglen with USDA and Dr. John Gulliver from the University of Minnesota. And again, my name is Seth Brown with NMSA. As I mentioned previously, this is a series where we have multiple webcasts that are focused on the issues and topics of stormwater ponds and basins. This series is brought to you at no charge through support from the Chesapeake Bay Trust, which has we are working under a grant from them to help spread information about issues such as stormwater ponds, everything related to MS4s and stormwater issues. This is the first webcast, The Problem with Ponds. We will have our second webcast, Ponds as Assets, next Thursday, September 24th, same time, 1 to 3 p.m. Eastern time, and there's a link that's provided there. This information will also be available at the end of this presentation, at the end of the initial presentation, and then during the Q&A session as well. We'll have other webcasts focusing on technologies as well as kind of the municipal perspective as and to wrap things up. Those have not been scheduled, but they'll probably be in the early to mid-October dates. A couple of housekeeping notes for everyone to know. The first is that this webcast is being recorded, but in case, just as an FYI for everyone who is providing questions and input. Also, a recording of this event will be made available on the NMSA website, and that'll be made available probably a week or so at the latest after the event is done. We'll also have a PDF of all the slides available as well that will be sent out and or made available at the NMSA website. And again, that link will be provided to folks. We do have PDHs available as well, and we'll send out a certificate that reflects that information. Also, I'm assuming many folks are familiar with these programs or these platforms. This is GoToWebinar. This is right now, because of the context that we're in here, it's a webcast. Only the panelists can speak. So if you have any questions, please use the question function, or you can raise your hand. There's the hand function if you have a question or a problem. But if you want to type out a question, because we're hoping to get a lot of interactivity here, please use that question function. And if you have any technological questions, please use the chat function. If you're having problems with us, if we get a lot of input on issue, then that's something that we'll try to fix on our end as well. Okay, So before we get going into this, we're going to launch into the overview of, give some background on NMSA, as well as going to set the stage on the pond decision framework. I want to see what, who's with us today. So we'll have a series of polls today, not too many, but we do have a couple. So the first one we're going to launch is asking what your professional affiliation is. So take some time, let us know. Okay, looks like we have, we're getting input here from folks. Okay, looks like we've got a lot of folks from the public sector, which is great, as well as consultants. And I'll share that. Here we go. So thank you for providing that input, and we'll be, as I mentioned, asking a couple of these different types of questions as we go along. So with that, I'll hand this over to Randy Neprash. Randy, feel free to kick things off for us.
Okay, thanks, Seth. So I'm Randy Neprash. I'm the vice chair of NMSA. I'm based in the Twin Cities in Minnesota, which is where I'm talking from now. And Seth, we should be on the next slide, I suspect.
Yeah, okay. I just have to,
So as Seth mentioned, this is the first in a series of 4 webinars, all focused on constructed stormwater ponds. So we wanted to give you just a bit of background, kind of the big picture behind the entire series. Stormwater ponds are the oldest of our stormwater best management practices or stormwater control measures. There was a period of time back in the 70s and 80s where this is pretty much what we knew how to do. We thought it was going to be sufficient. We all know better now. But these ponds were one of the first things everybody did. They're one of the, at least we thought, they were one of the simplest of our best management practices. We have them by the thousands. We've actually counted them here in Minnesota. Among our MS4 permitted cities, we have more than 14,000 constructed stormwater ponds. The numbers that I've heard for the Chesapeake Bay TMDL drainage area is on the order of 60,000 stormwater ponds. So we have lots of them. All these facts are true, but now we have new information about how these stormwater ponds are performing and can perform. And in classic fashion, we have good news and bad news. Next slide, please, Seth. So we'll give you the bad news first, which is we have some problems that have shown up that we didn't expect, we didn't know about earlier. And we're going to talk about 3 of them today. Pond sediments contaminated with polycyclic aromatic hydrocarbons, otherwise known as PAHs. Pond sediments that are releasing phosphorus in unexpected ways and significant amounts. In some cases, enough to offset almost all the other work that we're doing in a watershed landscape. And new demands on pond capacities because of climate change and changes in rainfall patterns. Next slide, please. But there's also good news, which is we have new techniques, new types of structures, approaches, controls that show the promise of being very cost-efficient pond retrofits that can significantly improve stormwater pond performance and function. And this is our teaser for the next webinars, because that's what we're going to talk about in some of the upcoming webinars. Next slide, please. So we look at all this and come to what seems like an unavoidable conclusion, which is that it's worthwhile to take another look at our ponds. We have problems in meaningful numbers, and we need to address them. We can't ignore them. And we also have these new opportunities to improve performance and improve the protection of water quality from our systems, all of which could lead to a reprioritization of what our organizations and programs ought to be doing in the near future. Next slide, please. So we're here to present these ideas to you, raise awareness, and test these ideas based on your opinions and feedback. We're going to be asking some feedback about how new these ideas are to you and your organizations after each presentation. But then we also want to explore building a national consensus on how to move ahead with these options. In some cases, the appropriate actions are entirely local in nature, but in other cases, there may be advocacy or policy work that's appropriate at the national level that NMSA can have a role in, and those decisions and that work will be much stronger if we have a unified approach to it. We also want to explore a decision-making framework that can help local implementers consider all their options and make sound decisions, which will be the decision-making framework that we're going to be talking about shortly. Next slide, please, Seth. So we wanted just briefly to cover who is NMSA, the National Municipal Stormwater Alliance. We're still quite new. So some folks know about us, but lots of folks don't. We are a national coalition comprised of MS4 permittees and focus solely on issues related to MS4 permits and running effective local MS4 programs. Our members are state and regional level coalitions of MS4 permittees, not individuals. We also have some affiliate members. Each of those state and regional members represent at least 5 MS4 permittees, though in most cases those numbers are much larger. And our affiliate members are consultants, technologists, law firms, manufacturers, or other types of private companies and public entities that are involved in the MS4 sector. Next slide, please, Seth. So here's some of the motivations behind the formation of NMSA, and they're worth looking at because this defines the work that we continue to do. MS4 permittees, there are lots of them around the country, and it was appropriate to have an organization to represent the permittees with a unified voice at the national level. We want to address changes in regulations both proactively and reactively. All of our programs can be much stronger and more effective if they're effectively connected and united to a certain extent. We want to promote stormwater as a resource, improve the public image of stormwater, and then create opportunities for multiple benefit and multi-use stormwater projects and programs. Next slide, please, Seth. Our vision. Every organization should have a vision. Ours is to provide clean water for the nation. We wanted to start small. And the vision will be met through the following supporting principles: provide and promote efficient programs, effective programs, and seek to have local decisions based on good science. Next slide, please. So our action areas are sector support and information. This is certainly an example of that function. Messaging and communication, education for local practitioners and programs, but also for the public, and then to address policy and advocacy issues, particularly at the national federal level. Next slide, please. So I talked about these state and regional level coalitions of MS4 permittees. All the blue states are the member organizations, where there are member organizations of NMSA. It's 20 states right now, and we have discussions going on in other states where you see these plus signs. It's another 8 or 9 states where we have found state organizations, and we're in conversation with them right now. Then there's also the affiliate members, which is something on the order of 8 to 10 additional members of NMSA. Next slide, please. And here's our current leadership. Scott Taylor from California is the chair. I'm the vice chair right now, and Jennifer Watson from Tennessee is our treasurer. Our relatively newly named executive director is Dr. Seth Brown. And with that, I believe, Seth, what's the next slide look like?
We're going to go over the pond decision framework.
Yep, and this is where I pass it to you.
Yep, thank you. Thanks, Randy. Okay, so we're going to take a little bit of time. Randy talked about the fact that one of the purposes of the what we're putting together here, not just in this for this webcast, but for the series overall, is to roll out this pond decision framework. The idea here is we want to provide a free resource to MS4s who are thinking about addressing their ponds, or maybe are on their way and they want to have a better idea of, or just another option to look at when trying to programmatically or systematically looking at ponds in their community. So again, this is the purpose. We're trying to provide this basis, and we want to look at 2 aspects here. The first is looking at what we're calling pond problems, and we want to be able to look at what corrections need to be made. There's just overall a critical situation when it comes to maintenance in the stormwater sector, and clearly stormwater ponds being the most ubiquitous of all stormwater practices out there, maintenance in this context is equally as critical. So we want to look at both the corrections for ponds that are not performing at the level they should be, considering there's regular aging obviously of any infrastructure, but there's should be a performance that is being provided by these facilities, and there's also going beyond. So enhancing pond performance, and that can be done through what we're going to learn today, and also in subsequent webcasts here. So again, this is just a straw man. This is an initial version. We're throwing this out there just to see what everyone thinks, and we might talk about this in the Q&A as well. But we were going to ask you specifically to remark on this. I'm going to go through a fair amount of slides fairly quickly. The point here is not to get into this too deeply right now, because we're going to ask you, again, to download this information and share with us your ideas. So we want to make this as interactive as possible. The framework that we've come up with, this initial framework, is based upon a couple of different sources. The one is the EPA Fundamentals of Asset Management for water utilities. And another is Trey Shanks with Freeze Consulting Group. Kind of took the fundamentals and reshaped them a little bit and grouped them together. We took that and we've kind of done a little bit more reshaping. So we've come up with 7 steps here. A lot of this is not rocket science, nothing new, but it's a just a, you know, it's a pathway that is based upon again, asset management and trying to be as programmatic or systematic as we can be with these. So first is just you know, obviously inventorying your data, then looking at pond status and determination. And I'll go through each one of these, but just want to walk through that this is a sequential framework. We also want to talk about things about condition and criticality. I'll talk about what that means, and then from that determine a risk perform a risk-based analysis focusing on corrections, and look at cost and risk for these corrections, and then also look at enhancements. So look at that as an opportunity-based analysis. And lastly, plan and implement. So that's it's pretty straightforward. So just going through each step real quickly. Again, we're not going to go through this in great detail, but again, just want to familiarize folks with this, and again, ask for your input later. So the first is to, again, we need to have an understanding of what's out there. And we're talking about not just identifying, locating the total number of ponds, but also come up with an understanding of the kind of problems that are in the community with related to ponds. And then what are the types of opportunities for enhancement as well. So we're talking about primarily two areas of what we thought about: physical, kind of the stability, the physical status and stability of the asset, as well as performance. How is it actually performing and functioning? So we want to understand where we are with not just, again, not numbers, but what kind of situation do we have in terms of our ponds in our program. Then we also want to understand what are our program goals, where do we want to go, and we have to understand that these goals will vary. Obviously, if you've got some parts of your community which may have sensitive water bodies, or you have a TMDL, or whatever it is, that your goals might be higher, you know, in those areas, or it might be tied to regulatory requirements. So there's an understanding that that when you're developing goals, these are going to vary by location and context. And categorize, you know, as you do your inventory, you can categorize all ponds and looking at the kind of status and the context of the goals that you have. So your categories could be, could be seen as level of service as kind of a analogy to that. So the lowest level could be, you know, everything's just failing physically and in terms of performance. That could also go all the way up to there's no physical degradation because it's been a well-maintained asset, and there's no reduction in performance. So it's performing as it should be, even if it's a 10-year-old facility. There should be some reduction in performance, but not for that age of that facility. And if you can go beyond that, maybe there's no degradation physically, and you're actually performing above the standard treatment capacity. And again, we're making an assumption here that when we talk about pond corrections, that's again taking ponds that are not performing or not physically stable right now, bringing them kind of up to snuff, and then enhancement would only occur if you've kind of met that threshold initially. So the next option here, or the next step, I mean, is to focus on what's called condition and criticality rating. So it really comes down to two questions. First is how critical are the problems, or another way of thinking about it is what's the consequence of failure? And these ratings can go from low to high impacts, as an example. Another critical question is, what is the probability of failure? So how likely are you going to have failure? So those two together, and again, these ratings can go from very poor to good, whatever makes sense. And these can be used together if you can plot this out by looking at that can help you understand how what's the risk profile for our assets. So clearly, if you've got a high probability of failure and you've got a very impactful failure, if it does fail, that's clearly a high risk situation. So this is a way for us to understand, again, which ponds are most critical in most need of correction. Beyond that, we can then say, okay, now we know what kind of corrections we need to make. What's the cost for those corrections? And we can think about that both in capital and O&M costs. And we can look at prioritization by taking that risk level of correction and then plotting that against this cost correction. So again, if you've got a risk level that's very high, that means that's something that's really needs some correction, and it's a low cost, then that would be that number one. It's a very good opportunity to correct, as an example. So that's why it's a green light there. And you can do this for your entire array. You can look at the same type of approach, but instead of looking at the risks and for correction, we could look at the opportunities for pond enhancement. Again, assuming that enhancements occur for those assets that are performing at or above the kind of the baseline for where those facilities should be at that point. So again, very similar. You could look at potential benefit across the top there, high benefit, for instance, and you have costs on the side there. You could have low cost, high benefit. Clearly, that's a, you know, when you look at benefit to cost, that would be the best opportunity when it comes to enhancement potential. So once you've got all that information together, then you can start to say, okay, now I know what I need to do for corrections. I know what I need, what my opportunities are for enhancements. Then I can lay this all out and start prioritizing across all of these opportunities and corrections. So you can obviously, some of the corrections can be done concurrently with enhancements, as an example. So again, I want to remind that folks that enhancement occurs only after the corrections have been made for those facilities. And lastly, understanding, once you've put the plan together, you understand what your total costs are, then you can seek funding assistance. Consider market-based approaches, especially for these enhanced assets, because that's where we can have excess treatment that could be traded or could be used in an offset context. And that we're starting to see more and more of that occur. So it's clearly an incentive for this type of investment. There are some other stormwater pond decision-making frameworks out there. One example is from Kitsap County in Washington, which is more of a flow chart. They're managing 300 of the 600 stormwater ponds in their county using this approach, really focusing on maximizing water quality improvements. But this it's a lot of the same information. What's the any maintenance issues are there? What's the context in terms of draining to sensitive water bodies? And any kind of history of other problems there too. So this is another way of approaching this. So this is something else that we could consider looking at. Another option is from EPA Region 1, which is similar to what we've laid out, just in a different kind of framework. And again, I'm not going to go through this in detail. Just want to recognize that there's many ways of going at this, and we're interested in your input on all of this. So I'm not going to go through all these questions here. These are evaluation questions that we want you to consider in the meantime. So there's a little bit of homework coming from this effort. And so the question is what to do now. So first of all, we provided slides on this framework. They're in the, if you go to your GoToWebinar kind of platform and app, there's a handouts area. So you have to click the handouts arrow to bring that down, and there's a PDF available there. If you click on that, it's going to open up a PDF within a browser, and if you do that, you should be able to download that PDF at that through that pathway. So so if you can do that, if you have any problems with that, we can always send it to you afterwards. So if it's not working for you, you can't find that, just let us know. So however you get the document, we want you to review this information. We want you to send us your thoughts. You can send it to me at Seth Brown at nationalstormwateralliance.org. Please include the following phrase: comments on pond decision framework, so I know what's coming in and I can organize these things the right way. But we really will utilize this input for this framework. We want to make it better. We want to get as much input as possible. And then once we finalize that, we'll make this available for free on our website. And I think with that, I think we'll move to our panel discussion. So Randy, you want to take it away from here?
Will do. Thanks, Seth. And it's worth telling people the PDF file that we're encouraging you to open up and download includes almost all of the slides that Seth just covered when he presented the decision-making framework. So that's what that content looks like and what you'll have when you open up that PDF file. So we're gonna move to our speakers. Our first speaker this afternoon, or today, is Dr. Barbara Mahler, a research scientist with USGS, the United States Geological Survey, who's going to talk about pHs in pond sediments and their relationship, particularly with coal tar seal coat. And that's the extent of my introduction. So I'm going to let Barbara cover additionally and hand it over to you, Barbara, please.
Great,
Hey,
thank
Barbara,
you very much.
I'll hand you the slides, all right?
That sounds fine.
Excellent.
Okay, give me a moment here. And there, so hopefully you should be seeing my slide, my first slide now. So as a brief introduction to me, I'm Barbara Mueller. I'm a research hydrologist with the U.S. Geological Survey National Water Quality Program. You may be familiar with the USGS, and if you are, you'll know that we are not a regulatory agency, nor do we make recommendations for regulatory action. Instead, our mission is to do objective, policy-relevant science. And the topic today addresses some research that we've been doing since the early 2000s that indeed has proved to be policy relevant. And I think it has particular relevance for the stormwater community. So I'm going to be talking to you today about polycyclic aromatic hydrocarbons, or PAHs is a much easier way to refer to them. If you're not familiar with PAHs, they are a large group of chemicals, but what they all have in common is they're based on the benzene ring. The benzene ring is an elegant, flat molecule that's created of 6 carbon atoms, each with a little hydrogen attached. Benzene is not a PAH, but it is the building block for PAHs. And if you think of a benzene ring as a 6-sided bathroom tile, and you start putting those bathroom tiles together with different numbers and different configurations, every one of those would be a PAH. So already you can imagine that there are a lot of different PAHs possible. In addition, we can substitute a carbon atom with a nitrogen, a sulfur, or an oxygen, or we can substitute hydrogen atom with an oxygen or a hydroxyl group or a nitro group. And so there's a very, very large family of PAHs and related compounds. Why are we concerned about PAHs? Well, PAHs have been shown to be toxic, mutagenic, or teratogenic, meaning causing birth defects in species ranging from algae all the way up to mammals. We know that 7 of them are probable or known human carcinogens, and 14 PAHs plus PAHs as a group are on the EPA priority pollutant list. So basically, PAHs are bad players. Where do they come from? Well, they are ubiquitous in the urban environment because we create PAHs whenever we burn or heat organic matter. So although they do occur naturally, we're creating a lot of them in the urban environment through car exhaust, used motor oil, atmospheric emissions, you name it. Lots of different PAHs in the urban environment. And so it's always been a challenge to try and determine which of these might be the most important sources. PAHs are a concern in stormwater ponds, and in particular in Minnesota, because Minnesota is somewhat unusual in that it's a requirement to measure PAHs in stormwater pond sediment before it's disposed of. And if the PAH concentration is high enough, then it has to go to a lined landfill, which can become very expensive. So, for example, in Burnsville, in Minnesota, 1/3 of their 270 ponds had sufficiently high PAH concentrations that the sediment would have to go to a landfill. A single pond can cost more than $150,000 for sediment disposal, and when you consider the number of ponds just in the Twin Cities metro area, this becomes a really staggering amount of money. So clearly there's a lot of interest for the municipalities to determine where are the PAHs coming from? Is this just a generic problem that we can't do anything about, or is there a controllable source? And we in the USGS have had the same question because we're concerned about PAHs in lakes and in streams, particularly after our research showed that PAH concentrations were increasing in urban lake sediment across the country. And we wanted to find out if there was one source that was more important than others. Our first clue came from not from our big national study that we were doing, but ironically from a local study that we were doing with the city of Austin. And they had measured some extremely high PAH concentrations in streams. So to give you some context to these concentrations, 23 milligrams per kilogram is a probable effects concentration. That's the concentration at which we would expect the sediment to be toxic to benthic invertebrates, the critters that are living in the mud. And they were measuring concentrations that are equivalent to those at Superfund sites, but just in small drainages in residential areas and not in all of those drainages. So why? Well, an enterprising technician with the city of Austin walked upstream, and what he found was asphalt. But asphalt doesn't have high pH concentrations, as we'll see in a moment. But where the pH concentrations were high, the asphalt had been coated with a black substance, and that black substance is called pavement seal coat. So seal coat is a consumer product. It's not part of the paving process. It's a liquid, it's a thick viscous liquid that is sprayed or painted on the asphalt of parking lots, of driveways, sometimes even of playgrounds. It's optional. It's designed or it's marketed as improving the aesthetics of the asphalt and of increasing the longevity of the underlying asphalt surface. You've probably all seen seal coat. You just never thought about it. There's two major flavors of seal coat. There's an asphalt-based product that used primarily west of the Continental Divide, and there's a coal tar product that's based primarily east of the Continental Divide. These look very similar, they're marketed similarly, they're applied similarly, but they're very different chemically because coal tar has about 1,000 times more PAHs than asphalt. So if we take a look at the MSDS for a coal tar sealant product, you can see that it's 35% by weight coal tar pitch. And coal tar pitch is a very complex mixture of chemicals, but they are primarily PAHs or related compounds. This is the same, very similar to the material that's in creosote. And we also know that coal tar pitch is a known human carcinogen. So let's compare the PAH concentrations in coal tar seal coat to some of our other urban sources, because simply source strength could be an important consideration. So here we're looking at concentrations in milligrams per kilogram or parts per million. I mentioned that asphalt has relatively low concentrations of PAHs. You can see that there are PAHs in things like tire particles. Fresh motor oil has low pH concentrations, but as we heat and burn that oil in our cars, we create PAHs, and used motor oil has relatively high concentrations. The asphalt-based seal coat is similar to concentrations in tire particles. The coal tar-based product ranges from anywhere from down to 35,000 parts per million to over 200,000 parts per million. So clearly this is a very strong potential PAH source. And to put this into context, 1 gallon of coal tar-based driveway sealant has about 100 times more PAHs than used motor oil. And we've gone to great lengths to educate the public about the importance of properly disposing of used motor oil and not throwing it down a stormwater drain. And yet very few people are aware of the high PAH concentrations in coal tar-based sealants. Another point of environmental relevance and relevance for stormwater ponds is that seal coat wears off. When it's first applied, it's black and shiny. It makes the asphalt look like new. But over time, with the abrasive action of car tires and in many parts of the country of snow plows, the seal coat, that dry sealant coating breaks up into little tiny pieces, and then it starts to blow away or get washed away by stormwater. So it doesn't stay where you put it, which means it has to be applied on a regular basis. Most applicators recommend reapplication every 2 to 5 years, but a lot of homeowners in particular reapply every year. We know that about 85 million gallons of coal tar-based sealant are applied every year in the US, which is enough to cover about 440 square kilometers every year. And that's because it wears off. Now here at the USGS, we've had some firsthand experience of this worn seal coat. We went out and we swept parking lots. I love my job. And what we found was this anecdotal evidence that we'd heard of asphalt-based products being used in the Western US and coal tar-based products being used in the Eastern US was reflected just in the PAH concentrations in the pavement dust from sealed parking lots. We also swept parking lots that weren't sealed in these same watersheds, and we found much, much lower concentrations. So because these are the same watersheds, we have all of the other same urban sources of PAHs. We have tire particles, atmospheric emissions, tailpipe emissions. What we don't have is coal tar seal coat. So it seems like the seal coat itself is indeed the result or causing these very high concentrations in the dust. Once we have this mobile dust, there are a lot of places that it can go. It can be blown off into adjacent soil, onto other pavement. It can stick to tires and be carried away. It can even make its way into your home and become incorporated into house dust. And that's a story for an entirely second presentation someday. But I'm sure what everyone here is interested in is the fact that it is in runoff and it makes its way into stormwater control, stormwater ponds, and streams and lakes. So here's a graphic example of that. These are a pair of stormwater ponds in South Carolina. And we have one stormwater pond that's draining an unsealed parking lot, and we have a second stormwater pond that's draining a sealed parking lot. And what we see is that the stormwater pond draining the unsealed parking lot, the PAH concentrations in that pond are about 1 part per million. So we can think of this as an urban background. We have all our other urban sources here. We're right next to a state highway. We have 45 times higher PAH concentrations in the other stormwater pond, and yet they're adjacent. Another graphic illustration of this are looking at some of the lakes that we have sampled for the USGS across the country. So we saw on parking lots much higher PAH concentrations for sealed parking lots in the east than in the west, as we saw earlier. And we were wondering, well, does this translate into lake sediment? So here we have Tannisbrook Pond in Portland and Palmer Lake in Minneapolis, very similar population densities, very similar land use, highways, shopping malls, and yet the PAH concentrations are about 20 times higher in Palmer Lake. Similarly, Decker Lake in Salt Lake City and Lake Ann in Reston, Virginia, similar land use, similar population density, and yet PAH concentrations about 20 times higher in Lake Ann. So this is compelling circumstantial evidence, but do we have any additional proof that these PAHs are actually from seal coat? Well, we can use the chemical fingerprint of potential PAH sources and compare those to the chemical fingerprint of the PAHs in the sediments in the ponds or in the lakes. And we can compare these. So what do I mean by a fingerprint? Well, here we're looking at the chemical fingerprint for coal burning emissions. And across the x-axis, we have 12 of the most common PAHs. And what we're looking at on the y-axis is the fraction of total PAHs that are made up by these individual PAHs. So for coal burning emissions, we have a lot of phenanthrene over on the far left. We have not very much anthracene. So this pattern is the fingerprint. Well, here's the PAH fingerprint for sediments from Lake Ann, and our correlation coefficient is 0.6. One would be a perfect match. So we have something of a match, but not a perfect match. Here's another example, the gasoline vehicle emissions fingerprint and the comparison to the Lake Ann sediment. Again, something of a match, but not a perfect fit. Here's the PAH fingerprint for Sealcoat dust. In other words, the particles that we've swept up off different parking lots coated with coal tar-based seal coat. And the match with Lake Ann is much closer. So this is suggesting that coal tar seal coat is perhaps a more promising, if you want to call it that, contributor to PAHs in the Lake Ann sediment than coal emissions and gas vehicle emissions. But realistically, probably all of these urban sources are contributing somewhat to PAHs in lake sediments. So we used a yet more sophisticated approach that was developed by the EPA. It's a mass balance statistical model that basically takes the PAH fingerprints of all of the potential sources and determines how much of each of them we should add together to best recreate the fingerprint that we see in the receiving sediment. We did that for 40 urban lakes across the US, which is what we're looking across the x-axis there. The y-axis is the PAH concentration. And this source apportionment model is telling us that those orange parts of the bar is coming from seal coat. On average, about 50% of the PAHs in the lakes that we sampled appears to be coming from coal tar-based seal coat on the basis of these fingerprints. Now, these are just the superficial sediments, but as part of our projects at the USGS, we collect sediment cores, long tubes of sediment, and we can look at those deepest sediments. Those are the oldest, and we can recreate trends in PAH concentrations going from the bottom of the core back to the top. And that's what we're looking at here. So these are sediment cores from 6 different, what we're calling new urban lakes. These are lakes that were urbanized in the last 15, 20 years or so. And you can see that PAH concentrations have gone up. And we've used this source apportionment approach to investigate the sources and see how those have changed over time. Here again, the seal coat profile is in, or fingerprint is in the orange. And you can see that for 5 of these 6 lakes, the upward trends are attributable to coal tar-based seal coat. The one lake that's the exception there down in the lower left is Railroad Canyon Lake in California, where A, coal tar-based seal coat isn't used, and B, look at the PAH concentrations. They're 100 or more times lower in this lake than they are in the other lakes where we see that coal tar seal coat fingerprint. So another group of researchers with the USGS has looked at PAH concentrations in stream sediment in Milwaukee. They were concerned about the ecological condition of streams across the city. They found that the only group of contaminants in the sediment that had a relationship to toxicity to test organisms were PAHs. And they used a weight of evidence approach to try and determine this PAH source. That included the fingerprint matching that I showed you before. It included different types of ratio analysis. It included the mass balance modeling that we looked at before. And on the basis of all of that, they estimated that about 75%, 3/4 of the PAHs in Milwaukee streams were attributable to coal tar-based seal coat. So one final piece of evidence, we could ask ourselves, well, what would happen if we eliminated use of coal tar seal coat in a watershed? Would it affect the PAH concentrations in pond sediments, in stream sediments, in lake sediments? Well, we had an opportunity to test that in Austin, Texas, because we had collected sediment cores in Austin prior to 2006. And in 2006, Austin was the first municipality to ban use of coal tar-based seal coat within the city limits. So we were able to go back and collect sediment cores after the ban and see if we saw a difference. So we're going to look at some sediment core profiles going from youngest sediments on the right to oldest sediments on the left, and the concentrations again are on the y-axis. Here's our core that we collected in 2000, and we see this strong upward trend in PAH concentrations. The ban started in 2006, and we went back in 2012 and 2014 and collected more sediment cores. We also have bed sediment concentrations that we collected before and after the ban. And overall, we see about almost a 60% decrease in PAH concentrations since the ban was instituted in 2006. So here's the pre-ban mean on the left and the post-ban mean on the right. And we used that source apportionment model again to look at PAH sources. And we see that even now, or even back in 2012 to 2014, the majority of the PAHs are still coming from coal tar seal coat. And that's legacy seal coat that was applied before the ban that continues to deliver PAHs to streams, to lakes, to stormwater ponds, and will continue to do so until all of those PAHs have worn off. So it's very similar to banning something like DDT or PCBs. We start to see a decrease right away. They are controllable sources, but we're going to see some legacy contamination last for a number of years. So that's basically the science that I'd like to share with you. And the main take-home point here is that coal tar seal coat is a major source of PAHs to urban sediments, and it also is a controllable source. We've worked with a number of people on this research, and they've come from different agencies, different academic institutions, and many of these researchers have also done independent research. I would say that the consensus of these independent researchers is unanimous that coal tar seal coat is a major source of PAHs wherever it's used. If you would like to find more information on this topic, we do have a website. We also have a couple of different fact sheets on this topic. I'd be happy to supply you with some of those if you have anyone you'd like to share those with. They're also available for download online along with all of our publications. And that concludes my presentation, Randy and Seth. So if you want to take my screen away from me, or I think we have a few moments to answer questions.
Yep, we do. And I encourage folks to continue writing questions. One question that's come up is, what has been the response by the industry on this? I don't know if that's something you get into, Barbara, but if it's something you can talk about, kind of curious to know what the response has been.
I can talk about it to some extent. There's been extremely strong pushback from the industry. There is a well-organized trade group called the Pavement Coatings Technology Council, or PCTC, who has been extremely active in trying to rebut the science. As a government scientist, there are a number of tools that private industry can use. There are Freedom of Information Acts, there's Information Quality Act challenges, and we have faced a barrage of these from the PCTC. The PCTC has also hired their own groups of consultants to use our data to attempt to come to different conclusions. We have rebutted all of their publications and all of their comments in journal articles. That's one of the reasons that I do show that last slide that shows of all of the different independent researchers who have come to conclusions that are consistent with ours. And the only entity or the only scientists who have come to conflicting conclusions are those that have been funded by the PCTC. Excellent. But this is not a new story, right? We've all, I think, experienced some of this level of response from people who have a financial stake in the outcome.
Yes, absolutely. There are some other
Seth?
questions that have come in, but I want to, Randy, if you want to ask your question, I'm going to launch this poll. So we're going to ask after each of these presentations, going to launch a poll to see if you guys can share your experience or your thoughts about what you just saw. So Randy, if you want to talk after I launch this poll, feel free.
Okay. So folks should consider this question and please answer it. I'll comment briefly on the earlier question. What's happened here in Minnesota is we've looked at the impacts on a kind of pond by pond basis, as Barbara mentioned, and we've done some of the courageous multiplication to estimate what the total costs will be, and the numbers are really impressive. We're talking at least hundreds of millions of dollars, as virtually every stormwater pond sometime will need to be dredged. So the first step for different cities here was to consider a local ban for coal tar sealant. And every time a city considered that, it became a meeting with their city council. And for multiple cities, the PCTC folks came out to attend and make their arguments before those city councils. Those were interesting meetings. We then moved to consider a statewide ban, which meant that our state regulatory agency, the Minnesota Pollution Control Agency, considered the wisdom of a statewide ban on Sealcoat, coal tar Sealcoat in particular. And there was a fascinating day-long session led by the commissioner of the agency to consider solely this issue. Barbara testified at that. The PCA did their own research, and that can be found online, and that was considered. And the pavement coatings trade organization had its opportunity to present their science and make their case as well. And at the end of the day, our state agency commissioner made the decision that the agency was going to support a statewide ban. They made that argument in front of our state legislature, and for a few years now, we have had a statewide ban on the use and sale of coal tar Sealcoat here in the state of Minnesota. But it wasn't without some contention and argument along the way. Seth, you want to talk about the poll results?
Yeah, I'll close that and then I will share the results right here. And you can see that most folks, about a third said this is entirely new, which is great. That's part of what we want to be able to do is we want to make sure that we're providing new and novel information. So it looks like this has been helpful that way. And then for a lot of others, nearly half or 40% said it's relatively new, aware but not yet addressed. So. And only 2% said it's not worthy of their attention. So that's a good thing. So thank you, Barbara, for sharing that information. And then I will, I'll bring this back and you can see we've got the next speaker. Randy, do you want to do a quick introduction on that?
Yeah, and I do want to comment though. These poll results show exactly why we wanted to do this webinar and thought that this was important. I mean, this shows that 75% of the folks that are listening, which is up to 158 people now from all over the country, are not really working on this issue yet. So that's worth noting. And with that, I mean, I'm beginning to feel as though we're running the risk of providing too much bad news to folks, but keep in mind, we'll get to better things in later webinars. But now we're going to move on to Dr. John Gulliver, who is a professor and researcher at the University of Minnesota, which means that I have the privilege of being able to work with John pretty frequently. And John's going to talk about phosphorus release from the sediment of stormwater ponds. And John, I will hand it off to you, please.
Thank you. Can you share my screen yet?
Yep, just did.
Okay, good.
We can see it.
Okay, thank you, Randy. Thank you, Seth. I am John Gulliver, professor of the Department of Civil, Environmental, and Geoengineering at the University of Minnesota. I do my research at the St. Anthony Falls Laboratory. I need to apologize for not being able to get my webcam functioning. It's been a struggle, but we're here. This research has been supported by the National Science Foundation, the Local Road Research Board from Minnesota, the Minnesota Pollution Control Agency, Department of Transportation, and the Riley Purgatory Bluff Creek Watershed District. So it's been supported by a number of people. I am doing stormwater research and maintenance, which we'll talk about today, infiltration, filtration, and pretreatment. So I do quite a few things related to stormwater. It is basically my life. Okay, it looks like you have to change the slides.
Okay, I'll look into that. I didn't think I'd had to do that. I think I've given everything to you right now. I will try to do that. There you go. You got it.
All right, I guess that's how I changed them. Okay. I don't do this research by myself. I have a number of collaborators. Jacques Finlay is a professor in ecology and behavioral biology. He's my co-PI. Tyler Olson and Vinny Taguchi are graduate students. Ben Janke and Purnima Natarajan are research associates. And Heinz Steffen is a professor emeritus. We are all interested in working on this problem. So the outline of my talk. Why is phosphorus important would be number one. I'm going to talk a little bit about it. Many people, possibly all of you, know that phosphorus is important, but I'm still going to talk a little bit about it. I'll talk about some assumptions that we have made about ponds and why these assumptions don't seem to be true. I will also talk about how I got into this problem, and that would be stormwater pond phosphorus concentrations, which came out to be really high, and I was really shocked by that. Finally, we'll talk about how fast is phosphorus release from the sediments and how we can stop phosphorus release, and I'll finish with some takeaway messages. So why is phosphorus important? Well, it is the limiting nutrient in freshwater bodies. What does that mean? Well, that means that the algae have everything else they need to grow, the algae and the plants. They have magnesium, manganese, potassium, and in most cases, nitrogen. If you add phosphorus to the water body, you get a huge bloom that looks something like this. The algae will grab that phosphate and that phosphorus, and they will use it, and they will grow like crazy. Now, with these algae blooms, you typically get blue-green algae, which is actually cyanobacteria. Cyanobacteria releases toxins, develops hazardous algal blooms, results in a soupy water body. So it's having too much phosphorus. Phosphorus is not a bad thing, except having too much phosphorus will not allow you to have a nice blue lake or a nice blue river or a nice blue pond. So one of the most famous problems that we have is Lake Erie. This is the algal bloom that happened last summer, I believe, in Lake Erie. And it is important because 40% of the lakes across the United States are impaired due to excess phosphorus. 46% of the streams and rivers are also impaired due to excess phosphorus. So it is a significant problem. In addition, you have things like hazardous algal blooms, where dogs die when they swim in the ponds and they drink the water from the ponds, and people get sick when they swim in the ponds. So let's get back to stormwater ponds. Stormwater ponds should retain phosphorus. They do a very good job of that for the most part. They capture the solids and associated phosphorus with the solid. So if you have dirt, it will have a phosphorus attached to it. If you have leaves and grass clippings and tree flowers, it will have phosphorus in its cells, part of its cellular makeup. Now these ponds are roughly 40 years old, 30 years old. They're getting pretty old. But we've made assumptions about these ponds. These are assumptions that were made in about 1980. First, our ponds are shallow. So that means they will not be stratified. They will be well mixed. That actually, a statement was made by the EPA early on in an EPA report that a pond could be up to 15 feet deep and still be well mixed. If they are well mixed, then they have high dissolved oxygen over the sediments because the surface oxygen is high because of exchange with the atmosphere. And you're mixing that, so that gets down to the sediments. If you have high dissolved oxygen over the sediments, you don't have any phosphorus released from the sediments, so the sediments can collect phosphorus from the material that it settles out. So this is how I got into this problem. I had someone from the Riley Purgatory Bluff Creek Watershed District come talk to me about measurements they are taking in ponds. Here we have a log axis on the y-axis of total phosphorus concentration, and the x-axis are different ponds. These are box and whisker plots for these ponds. 98 ponds altogether. And they told me that they had some really high phosphorus concentrations. They had some concentrations above 1 milligram per liter. 6 milligrams per liter in one case, 1 to 2 milligrams per liter in many cases. That shocked me because we are typically talking about micrograms per liter, not milligrams per liter. So I was thinking to myself, well, where the heck could this phosphorus be coming from? Is it coming in somehow? Well, we looked into it, and if you take a look at the red line, that's the 97% of the stormwater coming in is below that level. So that means that 97% of stormwater coming into the pond is below 0.38 milligrams per liter. So where did the rest of this phosphorus come from? Just for your interest, duckweed will stop forming when you get down to about 0.17 milligrams per liter, and impaired waters in Minnesota anyway are below 0.1 milligrams per liter. So where did this phosphorus come from? I'm thinking it has to be from the sediments. The sediments have a lot of phosphorus from what has deposited over the years. So why would phosphorus be released from the sediments? Well, it's related to oxygen and iron and the relationship between them. Under oxic conditions, that's greater than 1 milligram per liter dissolved oxygen. You have, now these, the iron chemistry is pretty complicated because you have 3 different ionic states and lots of chemicals that associate with them. But this is probably the simplest way that I can express what's happening. You have aqueous ferric ion, and that will combine, in this case, with phosphate ion, which is also aqueous, and it'll precipitate into a solid, which is strangite. Now, in anoxic conditions, that's less than 1 milligram per liter dissolved oxygen, you have strangite accepts an electron and develops and turns into ferrous ion, which is soluble, and phosphate, which is soluble. So when you go below 1 milligram per liter of dissolved oxygen, you tend to have phosphorus release from the sediments. That's why you want to have your ponds well mixed. That's why you want to have high dissolved oxygen over your sediments. So we went out and did some field sampling. We sampled the water column and we sampled the sediments. We've done 15 ponds. Here, these are some pictures of the 15 ponds we worked at. There are many different kinds of ponds. We have some high algae concentrations. We have some with duckweed. We have some without duckweed. We have some with macrophytes. They are all fairly shallow, and that's true of many ponds, most ponds. 2 meters or 6 feet would be towards the maximum. 0.5 meter or 2 feet would be towards the minimum. Here's the one result from one pond. It's pretty typical of the ponds which are problematic. This is dissolved oxygen. It's a diagram that where you have depth on the y-axis and date on the x-axis, and the colors represent the dissolved oxygen concentration. The bright red is a anoxic condition. That means conditions that can release phosphorus. Well, you can see that 85% most of the time in this pond, the bottom is bright red. The depth at the bottom is the bottom, the depth at 0 is the bottom of the pond. We also measure temperature and conductivity. And these are 3 charts: temperature at the top, dissolved oxygen in the middle, and conductivity, where the color represents different concentrations or different temperatures. Conductivity is a surrogate for chloride. And you can see if you get a conductivity above 400, it's probably chloride that causes that, because there's nothing else that we have putting in with such a high concentration. This is because we're in Minnesota and we tend to have salt, sodium chloride in our runoff in the spring. If you take a look at the winter, you have an inverse stratification. This is not so important, except that that's when the chloride comes in. The chloride comes in early spring, late summer, and stratifies the pond. You have 0 dissolved oxygen at that point. In the summer, you multiply that problem by having temperature stratification. So you have a temperature stratification and a chloride stratification. The only time when you have high dissolved oxygen over the sediments is somewhere between October and this pond, somewhere between, is in the month of November, actually. So many ponds are stratified at surprisingly shallow depths. You have a surface layer exposed to the atmosphere, and the result is it has high dissolved oxygen concentration. But you also have a bottom layer, which is not exposed to the atmosphere, so it doesn't get oxygen from the atmosphere. It is exposed to the sediments, where the sediments are using up the oxygen. That means you end up with low dissolved oxygen and phosphate release from the sediments into the water column. Why? Well, we think the main reason is because of wind sheltering. Wind sheltering results in, and chloride inflow in the spring results in chloride stratification, and wind sheltering results in temperature stratification in the summer. So let's talk about sheltering. This is what a pond looks like recently, shortly after it's been built. It's pretty clear. It's got some banks on it. You have, but you have the wind is able to get down and mix the surface. Actually, you can see some ripples on the surface of this pond. That's not the ponds that we're looking at. What we're looking at are ponds that are 30 and 40 years old. Around the pond, we have trees. We have trees and they have sheltering. They're sheltering, and the wind does not actually get down to the surface to mix the pond. We think that's the problem with these ponds. So how fast is phosphorus released from the sediments? Well, if you have a pond that is well sheltered, but your sediments do not release much phosphorus, then it's probably okay. So we investigated that. We sampled sediment cores. Here's our sampling crew. We sampled 5 to 6 cores from each pond, and we take 5 to 6 columns from each pond. We took them back into the lab and exposed them to an anoxic, low dissolved oxygen concentration in the water above the sediments, and to see how fast phosphorus or phosphate was released from the sediments. Here are the results for 5 ponds, and you can see that the variation in phosphorus flux is actually pretty large. P flux is the middle, is in the middle here. That's milligrams per meter squared per day. What does that mean? Well, it doesn't mean much even to me, except that I'm used to these numbers. But if you take that, multiply by the mean depth, and multiply by the days that you think are in the season, when you have phosphorus release being important, that would be 180 days in Minnesota, you end up with the impact on phosphorus if you did not have any release from the pond. Even though ponds have release, we're talking about what's the impact on phosphorus. And you can see that pond A has a 1.8 milligram per liter, quote, impact on phosphorus. That's pretty high. Pond C has 0.1 milligram per liter impact on phosphorus. That's pretty low. So these sediment analyses, the sediment tests, can tell you if you have a potential problem or not. So how can we stop phosphorus release from the sediments of stormwater ponds? Well, these are some concepts that we have. One thing that you can do is you can have alum treatment. That's been developed for lakes, but it's a new application for ponds. We can't put a big boat onto ponds, so we need some research into how to do this cost effectively, get the alum into the pond. Another possibility is iron filings treatment. We have discovered that iron filings, if you overload the sediments with iron filings, you can reduce phosphorus release. The iron filings and the alum are about the same cost. I don't know how it's going to end up, and I don't know which is going to be most effective. A third concept is pond mixing with aerators. Pond mixing might work well, but the problem is the ponds are so shallow that you end up just mixing a small area around the aerator. I'll have some examples if people want to see some pond mixing examples, but I think that actually might be the most difficult thing to do because you have to install a lot of aerators to actually mix a pond. Low level withdrawal is where you pull the water off the bottom of the pond, and then you let the surface water come down and refill with water that has high oxygen concentration. Finally, reduced sheltering. All of these things need research. So takeaway messages. My takeaway message to you would be, what can you do to detect pond problems? Well, first, observe the wind sheltering potential. Do you have trees all the way around the pond? Is the pond surrounded by big buildings? Those types of questions you might have. If the wind gets down to your pond is shallow enough that it's probably well mixed. Once you do that, if you find that you have sheltering problems, then you need to measure total phosphorus concentrations in the pond. The third thing to do if you have high total phosphorus concentrations in the pond is to monitor for stratification, that would be temperature and conductivity, and monitor the dissolved oxygen profile. Get out in the lake, measure stratification, and measure profiles, both of dissolved oxygen, temperature, and conductivity. And finally, you might want to consider sediment phosphorus testing, because that will be the final point at which you say, yes, we have a problem, or no, it's not a big problem. So we have found that our ponds work very well at removing phosphorus unless they're releasing phosphorus from the bottom. Are they phosphorus sources? Have they become phosphorus sources? In some cases they have. In most cases they haven't, but they are not as functioning as effectively as they would if they didn't have phosphorus release from the bottom. So I'd like to finish by advertising our Stormwater Updates newsletter. We talk about the research that we're doing at the University of Minnesota, and you can sign up at stormwater.safl.umn.edu. I hope there's time for some questions.
Yeah, John, I've got a quick question. I mean, there's multiple questions. One that comes up here that I think can be addressed quickly is, do you know if large rain events help with DO addition, or do you think that is actually increasing phosphorus downstream of the pond?
Well, large rain events would flush out the pond, and so that would increase phosphorus downstream of the pond. It would help with dissolved oxygen. And we saw one large rain event. We see large rain events in our profiles, and they help with dissolved oxygen, but the pond is so stratified that it's very rare that they will mix the lake entirely or mix the pond entirely. Does that answer the question?
I don't know. I'll throw that out there and see if people have any questions. And I've got one other question, and then I'll launch the poll. And then Randy, if you want to come to. So it's a very quick question. What is the minimum depth to avoid stratification?
Well, we had a pond with a 1/2 meter depth, like a 1.5 foot depth, and it was stratified. So I don't think there is a minimum depth to avoid stratification.
Okay, thank you. And we'll have time for more. There's a lot more questions came in, and then we launched this another poll. And Randy, I don't know if you have any thoughts that you want to share.
Yeah, I do. Thank you, John. As with Barbara, this is brilliant and really important work. I wanted to comment just briefly. John offered one pathway through which he got into this issue. It was a watershed district that had measured phosphorus levels in their ponds and sought an explanation. There's another example here in Minnesota where a watershed district close to the core cities of Minneapolis and St. Paul had a track record of 17, 18 years of really good work in terms of trying to address particularly nutrient loading through a wide variety of innovative, up-to-date stormwater management techniques. It was rain gardens, infiltration, rain barrels, you name it, these folks were doing it. And what they were finding was that they were not making as much progress as they hoped or expected based on all the work that they were doing. So that caused them to go back and look at their system to find if there were other phosphorus sources that were unexpected. And one of the things that they found, perhaps the most important thing that they found, was this phosphorus release problem from pond sediments. So essentially, you know, one of the things you were talking about, John, was what's the scale of the phosphorus that's being released. In that particular watershed district, the phosphorus being released from pond sediments was sufficient to offset all the other work that they were doing on the landscape, which was significant. So that's an important part of this story. I also wanted to do a little bit more advertising for SAFL, if I may. SAFL runs a monthly stormwater pond seminar. They've been doing it for a couple years now, I think, and it's going to continue on into the future. They bring in national experts, they do a presentation, then there's an hour-long panel discussion of local implementation folks who talk about the issue in more detail, and there's a wide range of questions that are addressed in the course of that panel discussion. So I would really strongly recommend for folks on the webinar, do a Google search under St. Anthony Falls Lab, and stormwater seminars, and you will find a wealth of interesting material, topics, and presenters. So I recommend that highly. And with all that, I was a little concerned about the bad news that we were presenting here, kind of an endless parade of problems. And it's kind of gratifying to see we were up to 158 people, and right now we still have 156 attendees, maybe a new record for people hanging on. But it's great stuff. And with that, we're going to move to our third presentation.
Randy, I was going to share
yes,
the
sorry. Oh, yes, I'm sorry. Please.
Yeah, that's all right. Okay. It looks like this is still something relatively new to a lot of folks. It looks like a significant amount of folks said it's relatively new, but not have yet addressed. But nearly a third are starting to work on this to address. So that's interesting. So, any other thoughts, Randy, before we move to the next?
Nope. But I think it's worth for Barbara's presentation. The folks that didn't think this was worth paying attention to was only 2%. This time it's 4%, a little higher, but still gratifyingly low. Let's
pretty
say.
Small. Yeah. Well,
yep.
and everybody, thanks for sending in questions. Continue to do so, and we'll have one more poll when we're done with the last presenter, and then we'll have a Q&A session. I'll also say that I think even if we go a couple minutes past 3 o'clock, as long as it's okay with the panelists, then I think we can keep going. But anyway, we don't have to be. I'm a little bit loose on time myself, so it's those who know me know that's the case. Okay, so all right.
Okay, thank you, Seth. And with that, we're going to move on to our third presentation, which is the challenges faced in terms of stormwater pond capacity and design because of climate change and changes in rainfall patterns. And for this, our speaker is Dr. Glenn Moglen from the U.S. Department of Agriculture. And with that, I will hand it off to you, Glenn, please.
Okay, I'm thumbs up that you can hear me, yes?
Yes, we can. And I'll just mention that I have to say a quick note here that Glenn was my master's advisor many moons ago, and is a great researcher. And it's great that we're seeing both the water quality aspects, and now we're going to talk about some of the water quantity aspects. So go ahead, Glenn. I'll get out of your way now. Okay.
Sure. So I no longer can see my camera or my picture, which is great for me. Just want to confirm you can see my PowerPoint slides now.
Absolutely, we can see everything.
Okay, very good. And when I move my cursor, you can see that as well?
Absolutely.
Okay, great. All right. So thanks so much, Seth, for inviting me, and I hope I'm not going to lose too many attendees while I'm speaking. The pressure is on. Like Dr. Mahler, I would like to point out that USDA is not a regulatory agency. And furthermore, this research actually dates to about 2013, 2014 timeframe when I was still a professor at Virginia Tech. So these views certainly are, the views I expressed today are not those of the USDA or the Agricultural Research Service where I work, but are really just mine. And I certainly will invite whatever questions folks have, but I am not a representative of USDA as I'm speaking here today. I'd like to acknowledge my co-author, Eliana Rios. Eliana was a master's student with me at Virginia Tech at the time of this research. So just to give you a bit of sense of what's coming, I'll explain the motivation for this work, some of my methods, try to emphasize the results. Would like to point out that this is all based on a paper that was in the ASC Journal of Hydrologic Engineering back in 2014. So if you have any specific questions, I certainly would refer you to that paper for more details. So what's the motivation for this? So much of the attention on climate change is focused on, you know, those really out there extreme events. But stormwater infrastructure tends to be designed for the kind of a different category of events. They certainly are big events, but they're not the monster 100-year events. They're the more frequent 2, 5, and 10-year events. And so this work was really motivated just simply to examine what do climate change models have to say about both storm intensity and storm volume, and how, and since those things, intensity and volume, are what are the drivers of infrastructure design, how does climate change, how does forecasted future climate affect how we would approach sizing stormwater infrastructure? So what did we do? We went to the NARCAP data set. NARCAP is a North American Regional Climate Change Assessment Program, and they had a number of basically RCM, GCM, Regional Climate Model, General Circulation Model pairs, and we chose 4 here so that we could play with both different, certainly 4 different regional climate models, and actually be able to compare that with 2 different GCMs that were driven. And we downloaded data from the NARCAP website, 30 years of data, 3-hour time step, and the data were divided into a present, which was basically 71 to 2000, and a future of 2041 to 2070, so 2 30-year periods. And we aggregated the data into a number of convenient time intervals, 3, 6, 12, 24, 36, and 48-hour intervals. And for each of those 30-year periods, and so this is both the present period and the future period, we identified in each year the largest event for each of those durations. So we've got a lot of moving parts here. We've got a current and a future. We have different time intervals from 3 to 48 hours. We have annual observations of the biggest in each of those categories. And we're basically building a time series from that on which we can do frequency analysis. So we did, we assumed a log Pearson 3 distribution. This is really just completely analogous to flood frequency analyses. And we're dealing only with 30 years of data. We have 30 observations in a given time series, 30 for the present, 30 for the future. So we have decent degree of confidence in how well we're estimating the 2, 5, and 10-year events. To stretch it to much longer would be a stretch. And so if you've got rainfall intensity on the vertical here, and you've got duration on the horizontal, the circles that you see here correspond to the different time intervals that we worked with. So the leftmost circle is at 3 hours, then 6, 12, 24, and 48 hours. And we fit a regression line through those points, and we assumed, as is typically assumed, that intensity is just a power function of rainfall duration. And so we basically, for a given GCM, for a given present or future, we were able to derive the coefficients C and D shown here that describe the slope and the vertical location of that line. And then we made the following assumption. We recall we have a present and a future. So we can calculate a ratio of what that fitted line looks like. The future line is on the numerator. The present line is here in the denominator, and from that we get a ratio that's a function of the model, the duration, and the frequency. We then took that ratio, that's this guy here at the far right of this equation, and we multiplied it by the NOAA, the actual observed NOAA Atlas 14 value for duration and for the same duration and frequency, and that gives us sort of an estimate of a future intensity. And I failed to say this. This is all for work essentially just north of Washington, D.C. You might as well consider it Baltimore. It's actually in Montgomery County, Maryland, where I happen to live. And so to give you a sense of how this looks for the ECP GFDL model at 3 hours duration and 2-year return period, for the future, we calculated the 18.3 and the 0.569. For the present, we have the numbers in the denominator here, and there's a 1.14 multiplier. So basically, the 3-hour, 2-year storm looks to be about and bigger in the future than it does in the present. So we take that 14% bigger, and we go to NOAA Atlas 14, and we look up the present day value, which is 15.6 millimeters per hour, and we get an estimate of a future precipitation for the 2-year, 3-hour event of 17.8 millimeters. So not very complicated. Wanted to get a little bit more sophisticated here because we're interested in the distribution of the storm. We're interested in the most intense part of the storm. So there's a little bit of black magic going on here. On the far, we have this log-log relationship of intense duration, a common model that's fit to shorter durations, because it's often observed that in precipitation frequency, the log linear behavior tails off, and so this sort of functional form fits that well. So we simply made a decision that this transition point would be at 1 hour, and we said we're going to fit a model that's continuous at this transition point and has the same slope at this transition point. And so from continuity, so that's basically having the two equations agree at this point. From continuity, we get, this is just algebra here, and at a transition point of 1 hour, we see that A is actually equal to C times the quantity 1 plus B. So we're basically, I should say this now, we have the C and D that we're actually calibrating from observations. We do not, in the NARCAP data, we cannot see below 1 hour. We can't even see below 3 hours. So we can't see what's going on here. So we're assuming this form, we're assuming a transition at 1 hour, and we're going to let those assumptions allow us to calculate the A and B. So back to the math here, from continuity of slope, we get this. I'm going to go through this quickly. I encourage you, if you don't trust my algebra, to go look up the paper, and you can work this out yourself. But like magic, B becomes a function only of D, and A becomes a function of C and D. And so by virtue of saying that the transition point is at 1 hour, and by virtue of already having calibrated C and D, we have estimates of A and B. So in other words, to go back to this figure, we know what this entire curve looks like for durations that go from, let's say, 5 minutes all the way to a day or two. All right. So, and this slide just says what I just said. Bottom line, we fit the IDF curve for the log-log linear behavior, and that allows us to calculate the region for very short durations where we don't have that log behavior. And so here's where the rubber meets the road. The two solid lines that you see here are are just directly from NOAA Atlas 14 for this location that we were working in, basically Rockville, Maryland. And you see that the lower solid curve is the 2-year event. The higher up solid curve is the 10-year event, which you would expect intensity is going to increase with return period, the length of the return period. And this dashed line that you see turns out to be from our modeling approach, the 2-year event for this particular RCM GCM pair. And so what you see is what we commonly saw is that the 2-year event of the future is bigger than the 2-year event of the past, but actually it's the much shorter durations that are more inflated, and that by the time you get out to the larger events, the difference between what the models are saying and what's been observed is not so great. So so we've developed a set of these curves for the 2-year return period, the 10-year return period for 4 different models. Let me come back here for a moment. I can go to this dashed line curve and I can pick off all sorts of durations, very short ones, which is why I did all that algebra a few slides ago. So I can estimate the 5-minute, 10-minute, 30-minute, 1-hour return period, durations, what the intensity would be. And I can basically build a design storm centered on 12. So this is a 24-hour design storm that's centered on at the 12-hour point. And I take those most intense intensities and I artificially build a design storm that this is basically saying, I've got normalized depth over here. This is basically saying that my most intense part of my storm is occurring at 12 hours and it's set up by less intense parts for the rest. But that's all taking the, say the 2-year event or the 10-year event, whatever it is, and looking at the intensities that you've calculated, and you build this artificial design storm that represents the most extreme case for all possible different durations for a given frequency. So we have depths as indicated here, and we have storm distribution as indicated here. Now we're ready to model. So what we did was we took our design storm. You saw my S curves here, and we also know what the precipitation depth of the future is, and we throw them into a watershed, and that watershed has some unregulated or unmitigated flow that enters into a pond, and the pond really has this can be characterized by some total storage that it needs in order to release a controlled discharge. And so we sized our ponds not for extended detention. They were just peak discharge control ponds. We basically took our 24-hour design storms, we threw them at a very generic watershed, and we ran that for both present and future, and used the designed a pond so that the future discharge matched the present discharge, and we noted what the maximum storage would have to be. So this shows you an example. We have our current uncontrolled 2-year event, the black line, and then we have for the 2-year for a particular climate model, we have the 2-year uncontrolled flow. And so again, we're trying to do peak discharge control. So we're trying to bring whatever, we're using this red hydrograph as inflow to a pond, we're trying to bring it to the peak discharge of the black pond here. And we're going to note what the storage looks like. So it all boils down to this last slide here. And so a little bit of introduction so you understand what you're looking at. We have the uncontrolled flows in the top set of graphs. We have the controlled flows in the lower, and we have the maximum storage that was observed or needed, I should say, in the lowest set of graphs. Across the bottom, we've got our 4 different models. And then I've got color codes here. The blue is the 2-year event. The red is the 10-year event. And then you see 3 different stacks of bars here. The first bar represents what happens if I mess with the storm distribution, but not the depth. I'm going to use the current observed depth to drive things. What happens if I use the current depth, but I use just basically the current storm distribution? And then what happens if I apply the third bar is what happens if I vary and use both future distribution, storm distribution and storm depth. So there's, again, a lot of moving parts here. So let's go through this one by one. The first thing you note is that the general shape of the bars that you see varies considerably from model to model. The second thing that you see is that, at least for this climate model pair, we're cooked. I say we're cooked because it's both the increase in distribution and depth. You'll notice that at the 10-year level, with the both going on, you see these really high peaks for when both the depth and the distribution are acting together. So in other words, they're superimposing on each other, and they're collectively making life worse, or basically the needed storage that you have much bigger, the uncontrolled discharge much bigger. For the next model, I would characterize this particular climate model pair as much ado about nothing. You notice that the bars are all essentially of the same height, so there's really not much going on for this particular climate model, regional and global climate model pair. In this particular model, you'll notice that the depth bar and the both bars are essentially the same height. So it's really just the precipitation depth that is increasing, but the intensities are really not changing. So there's a lot of variability here, depending upon which model you look at. And then finally, this last model pair, you can see that actually the last bar, the one that represents both precipitation depth and distribution changing at the same time, is actually lower than when depth alone is applied. And so that's saying that actually the storm distribution is less intense than what's been observed historically, and that's actually acting, even though there's more precipitation landing, it's coming at a more uniform way, and therefore you need less storage when both are acting. So we get really 4 different stories across these 4 different climate models in terms of what it's saying about what future capacity has to look like. And so to conclude, stormwater infrastructure tends to be designed relatively relatively frequent precipitation events, 2, 5, 10 years, and I looked at 2 and 10 in this particular analysis. Both the storm distribution and the depth may be changing with climate, and they act independently of one another in terms of what they mean for peak discharge. And so there are vulnerabilities that exist because there's a lot of model variability going on here. I walked us through 4 models and had 4 different stories. In general, future storm depths seem to be larger, in some cases only modestly larger, but in general, they are larger. The distribution was more changeable, and we saw distributions that could amplify the depths or could actually modulate the depths. Well, this was just in case there should be questions. So I'll end there, but I'll be happy to entertain your questions, and thanks for the opportunity for being able to present to you today.
Thanks, Glenn. Randy, do you have any immediate questions? I've got some that have come in, but I wanted to defer to you first.
Yeah, why don't we take the questions that came in, please?
Well, the most specific and I guess easily addressed question is, how does all the work that you've done, Glenn, how does it, if you want to boil it down, or how could it or how should it inform how design is done in the future? Is it are we doing it the right way now? Is it what are some general? I know that that's a deep question. You can go many places, but generally speaking, how should we be taking a different approach when we're thinking about stationarity versus non-stationarity?
Yeah, well, that's the key word right there. We're dealing with the non-stationarity of climate. It's hard to know. This is anecdotal. This is basically several different climate models in the Mid-Atlantic. We did not explore larger across the U.S. So that would be an interesting study, would be to do this across the U.S. and see what's going on. But at least in the U.S. Mid-Atlantic region, this work is suggestive of stormwater ponds that have been sized based on current climate are probably in most cases going to be coming up short if future climate is well forecasted by the different climate models that are out there. So in general, this would be suggestive of there being an undersizing of stormwater pond capacity if you're really trying to control certain flood events. With greater frequency, you're going to be seeing storms of that magnitude. So these ponds are going to be underperforming from a charge control perspective. Okay,
and just a quick follow-up of my own is, do you see this work was done in 2014, it was published in 2014. Has there been better data or better modeling that might, if you were to rerun this and go through this again, that would, so the point is that was a point in time when we had certain data sets and certain models. If you ran that today with a different data set, do you think that you'd come up with similar results, or is the data that much different, the models that much different now?
Yeah, it's a fair question, and whatever I say right now, it's just conjecture. Climate modeling is something that is very aggressively being pursued in academia and across the world, and so I can only expect that climate models have improved, and of course one could look at ensembles as well, which are shown to in general be more reliable than any one model. This is a snapshot of data that we obtained in the early teens of this century, and so it's quite possible things have changed. I think I'm going to go out on the limb and say I think that a lot of what we found would still be borne out by newer data. I'm not hearing that newer models are predicting smaller events or less intense events, and those are the things. The climate models are predicting more rainfall, and when it comes more rainfall. And so those two things act to give you the larger peak discharges. So I think that the general findings here would hold true even for newer models. Of course, the numbers would change, but I do believe the general findings would hold true.
Okay, thank you. There are some other questions for everybody, but I want to launch this last poll. And I'm wondering if, do you have any thoughts at this point, Randy, that you want to share?
Well, I'm curious, Glenn. Cities are asking project applicants to do stormwater calculations for their sites, and then you base their pond or other infrastructure design decisions on those calculations, usually based on relatively simple models. Based on your work, should we be looking at different inputs for those models that we're expecting project designers to use? And are we approaching a point where there will be standardized recommendations as to what those inputs and other parameters should be for that sort of modeling as the basis of design work?
I think you don't want to design with a locked-in mentality that climate is stationary. So either two thoughts that go with that would be, one, if you're designing based on current numbers on observational data, you may be under designing. It's possible you're even over designing, but more likely under designing for what future climate may look like if you're looking for the same risk profile coming out of your pond. At the same time, maybe you should be thinking in terms of your design. Is there a way that you can build your design with flexibilities so that perhaps retrofitting may be something that's easier, a way to add storage quickly, or maybe resize the outlet structure at smaller cost. If you're going to go with a pond as your main design, is there a way you can think about your design in the future such that retrofitting could be done at a relatively modest cost?
Interesting. Thanks. Interesting results on this poll, Seth.
Yeah, I agree. It's kind of a trend that we're seeing here, that it seems like these topics and these problems and challenges are relatively new to many of us, but we're aware, but we haven't addressed yet. But I think it's interesting that there is a significant group that's working to address this. I'd be interested to know, what does that mean? You know, how is it being addressed? You know, so that's just a reflection.
Yep, I agree.
So I will show. So I think we don't have a whole lot of time left. Randy, do you have some thoughts about? You want to wrap things up? There's a number of questions that have come in for all the presenters. Any thoughts?
Well, I think it'd be nice to take a look at some of the questions, but we are at our appointed time. So I want to say thank you to all the presenters. Also say thank you to all the folks that have stayed with us during the webinar. It will be available as a recording, and we should spread that word far and wide. You can see the information on the slide being shown right now for the next in the series. But with all that said, why don't we take a shot at a few of the questions, Seth?
Okay, I'll do a
Maybe
couple.
go
And I'll
for
just
another 10 or 15 minutes.
Sure. So Barbara, just a question that came in, a couple that I think you could answer quickly. One is, how many municipalities have banned coal tar sealant? So that's the first question. And then the second would be, what led to Austin banning the coal tar sealants? There was a water quality concerns, for instance. So I think that's kind of
Okay.
paired questions
Sure.
for you.
So 3 states have banned use of coal tar seal coat: Minnesota, state of Washington, and Maine. There are a large number of municipalities and counties that have banned it. I can't detail them all. I know that they include the city of Washington, D.C., the city of San Antonio. There are about 40% of the counties in the state of Maryland have banned the use of coal tar seal coat. If people are interested in learning more about the bans, there is a website that Tom Ennis has put together called Coal Tar Free America that gives a lot more information on those bans. And I think that also
And Tom Ennis is with City of Austin,
Minnesota
is that
PCA
correct?
has some information on that. And then the second question was, why did Austin ban these coal tar seal coat? The city staff was very proactive. They had gotten this grant from EPA to measure contaminants in small streams. They discovered the PAH problem. They were the first to connect the dots with the coal tar seal coat. And I think because they had such an active watershed protection agency within the city, they convinced the city council that that was what they felt was the right thing to do.
Excellent. And you mentioned the name Tom Ennis. I just want to mention he's with the city of Austin. Is that correct?
He is with the city of Austin. The website is not associated with the city of Austin. It's something he's put together on his own, but he's compiled quite a bit of information on this topic in his Coal Tar Free America website.
Okay, great.
Seth, I wanted to speak to that question just a little bit, if I could.
Absolutely.
There's a larger regulatory framework around this issue. And in the state of Minnesota, there are essentially 3 components to it. One is there's a recognition by everybody that stormwater ponds fill up with sediment over time. That's virtually inevitable. And that as they fill up and the wet volume is diminished, the water quality functionality of the pond is also diminished. So how that's reflected in Minnesota is that all the MS4 permittees are now required under the general permit to assess their ponds, particularly for depth, to see how that water quality functionality is holding up. And as it is found to be lost, the permittees need to respond with a program to dredge those ponds and restore that functionality. So there's the first piece. Second piece is that as ponds are dredged, the state requires a permittee to test the sediments before those sediments move to whatever is going to be their fate in disposal. And then the third link is the state has quantitative thresholds for PAH concentrations in those pond sediments. And if a permittee finds that those thresholds are exceeded, then those sediments have to go to something like a lined landfill, and you end up with very significant transportation and disposal costs. So you link all those regulatory requirements and you get a significant situation, for lack of a better term. I'm kind of curious, and NMSA may do some work looking at other states in the country to see what the regulatory environment is in other states right now. Sorry, but that seemed worth saying.
Absolutely. No, I think it's a great point. John, I don't know if John's still on or not. John, you're muted if you're still on. Okay, great.
I am. I'm still
Okay,
on.
great. Okay, two quick questions for you. Oh, I don't know how quick they're, but I think they're somewhat related. One question has to do with the potential competing interests between if you denude all the vegetation, around a pond, obviously that's going to lead to increased temperature. So is there an issue related to, you'll have a sheltered pond that's well shaded, or you could have a non-sheltered pond that's well mixed, but could be warmer. So that's the first question. And the second question is someone noted that in Florida they've been using alum, and there's always been concerns about copper sulfate having downstream impacts. Is there the same kind of concern related to adding iron or iron filings in the context of addressing this problem? So those are the two questions that came up.
Okay, thank you for those questions. I'll answer the second question first. Iron is fairly ubiquitous in the environment. We are used to different kinds of iron. We drink iron all the time. It's really not a problem until you get to really high concentrations. So iron is not a problem, and that is one reason that we were looking at that as another way to basically seal these sediments. So that might be something that you want to try. The other question with regard to sheltering, shading, and temperature. If you have a shaded pond where you're shading much of the pond, that's a pretty small pond. And so you are really not going to be able to have mixing in that pond unless it's really wide open. So for these really small ponds, I don't think there's much that you can do aside from possibly one of the other issues, which would be sealing the sediments or having a withdrawal from the bottom. But temperature is important in these ponds. If temperature is important that you want to have a lower temperature release, yeah, you need to somehow deal with that. And there are various things that you can do. I don't have time to talk about them right now.
I wanted to make one other quick comment though, which is I've seen and heard some discussion about opening up some of these ponds for exposure to the wind. And you don't have to take down all the trees by any stretch. Essentially, you look at the direction of the prevailing winds, and if you are going to take down trees, you do it in corridors. So you can take down maybe only a quarter of the trees around the pond and still open it up to wind exposure.
Thank you, Randy. I took that out of my presentation.
Fair enough. Okay, and Glenn, there's a follow-up question here, and it's just basically how transferable is the approach that you took? I assume that you could do this type of analysis throughout the country in any different places. And if that's the case, has that been done, or are there been other research that's similar to this to look at other, and other regions? And do we see any trends related to that?
Wow, all really good questions. The transferability, which I guess I would interpret as how easily could this be done at a different location? The answer is that's quite straightforward. That's easily done. Has it been done? I should know, but I don't. A little bit of a lit search would reveal the answer to that. Certainly, just starting with my paper and seeing what papers cite mine and what those papers are about. what was the last part of that question? Can you remind me?
I was asking, is it if it has, if this has been done, or if a similar work has been done, have you seen any similar results, or do we see places where it's going to, that precipitation is going to drop, and therefore, there are what are the implications of that, so trends and implications.
Yeah. So I think there are few too many degrees of freedom right now to speak with any authority. Anything I would say would be conjecture. I think if you go with what's broadly said, I would expect that the general trend of increased intensity would hold true across in a rather general way. Actual depths could change, but I think in general those are going to be amplified as well. So I think that those are the trends that you'd find, but you would have to run this out. You would have to look in a number of different settings and see what you find. It's quite variable geographically. So I'm reluctant to guess. I tend to think that what I found would be what would be generally found, but I don't know that I'd want to go, even that is conjecture. To say anything more would be probably too much of an extrapolation. I'm sorry, I'm hemming and hawing here.
No, I understand. That's interesting.
I think you have to do the analysis to see.
Yeah, and I'll just say there were several questions that were similar. So I'll just generalize this. And it's, again, I think I asked it, I think before, but let me revisit it real quickly because some questions have come in after that. How do you take your results and potentially bring them into design guidance manuals and whatnot? Is there any, I mean, for instance, if this was done in Montgomery County, has Maryland looked at this information and tried to integrate it into their design manuals, or does Montgomery County?
I know this work was funded partially by the Maryland State Highway Administration, and they were interested in how their designs might behave in the future. So we were trying to build in some climate model data that they could use in their modeling, just as they used the NOAA 14 data. I am not aware of a policy or a design policy that's in place that approaches this. I've heard anecdotally of places where people will choose maybe the next larger event. So if you're dealing with 2-year events, they'll go to the 5-year event, or if it's 5, they'll go to 10, and they'll use that as a way of adding a little bit of a
Safety factor.
Yeah. Safety factor on top of what they're doing. But I think that's been done almost more for just sort of having a sense of magnitude of change. I don't know that it's actually even part of policy yet. So where this should go is this is again me speaking, not USDA, but if we're going to design structures, whether they're ponds or culverts or what have you, if we're designing them with a design life of 50 years or more, we are designing for a climate that we haven't yet seen. What is the risk of failure of that structure if it's undersized is the question that you have to ask. I think if a pond fails, that's one kind of failure. If a culvert fails and a bridge floods, that's maybe a different kind of failure. So I think you have to consider what is the consequence of failure? What is the risk to life or property for failure? And then I think that has to factor into what you should do.
Yeah, that's great thoughts, Glenn. I wanted to mention, and Randy, you might want to build upon this. I know you referred to Atlas 14, Glenn, and I'll just mention that NMSA has been active in advocating for an expansion of Atlas 14 to be performed across the entire country and done at a regular interval because of the changing precipitation patterns. And I know that Atlas 14 it looks at data up to today. It does not look at future projections, which is why the utility of what we've been doing. But I know that anecdotally we've heard that some states and municipalities are just adding on some kind of maybe 10 or 20%. But again, I haven't seen anything that's been in that, and maybe it's out there, but anything that's in policy or guidance that says thou shalt do this. It's just more about, they're looking at trying to add the safety factor and kind of what you said. So Randy, do you have any thoughts on that? I know that you're passionate about the Atlas 14 topic.
I do, but I think as much fun as this is, I think it's time to wrap up the webinar.
Oh, good things were said.
Yeah, sorry about that. Really want to thank Barbara and John and Glenn. Thank you so much. Seth, thanks to you too. Thanks to our audience and all the folks who stayed with us. And please join us again next week, where we'll do this all again and in a somewhat more positive and encouraging fashion, we hope. And with that, we will say goodbye.
All right. Thanks, everybody.